Hi, everyone. So just wanted to give you kind of a brief overview of momentum and to kind of launch us into that topic. We're going to be doing a couple of more examples along with the Khan Academy stuff. We're not just going to use that to really dive into this very, very important topic. And we know that force equals mass times acceleration, right? So we've got that from Newton's laws. Force measured in newtons equals mass measured in grams or kilograms times acceleration, which if we're doing gravity, it's 9.8 meters per second squared. But if we're working on other uh, types of equations, the acceleration might be different if it's linear, like side to side, or if you're in a car or train or airplane or something like that. So we also know from eighth grade physical science class that there's something called the law of conservation of mass. And there's also the law of conservation of energy. So all the energy that was created at the beginning of the universe, it's still the amount of energy that we have. And typically in a system, we have the same amount of energy that results at the very end of whatever we're looking at that we had at the beginning. So energy and mass changes form, changes shape, but it's neither created nor destroyed. So in our universe, the same amount of mass, same amount of energy that we've had since the beginning is going to be the same amount theoretically that we have at the end. We'll talk about entropy in the spring. So here in a big classical Newtonian world, it makes sense that this Winnie the Pooh, I don't know what this is from. This thing was created using products and plastic, as we're going to talk about with Hooke's law, plasticity and plastic objects that came from some other type of object. In this case, probably a few water bottles and other kids' toys that hopefully were recycled. It's got some screws in the back that look to be nickel or some type of metal. So anyway, all those things came from places. Nothing is created or destroyed in the grand scale of the universe in terms of the amount of stuff we have, the energy or the mass. Momentum is kind of like that. So momentum, we actually have a law of conservation as well, and we call it the law of conservation of momentum. And again, we're going to talk about this a little bit more after this brief intro. But the concept is that in a system, and when I say system, I mean when something's happening. So pretend I have, I'm got all my kids' toys here. Pretend I have Zane here from Ninjago, Lego Zane here, and this pumpkin, and they collide. That creates a little system, right? So Zane and the pumpkin collide and create a little system. In that system, the amount of momentum that Zane has as Zane approaches the pumpkin and the amount of momentum that the pumpkin has is going to be the same amount of momentum at the end as their initial momentums. So the momentum is just like mass or energy. It doesn't change because they're all related, as we're going to see. So F equals ma is very, very fundamental because it relates to all these other equations and concepts we're going to be talking about, including the equation for momentum, because momentum's equation is a very, very silly P equals mv. P equals mv. Momentum is P. Why? It's a complicated subject. I'll put a link down below in the show notes here. But basically, the idea is that in the 19th century, Germans ruled the scientific world in the late 19th century, and they got to make all the rules. So the Germans and the French decided to make momentum P symbol-wise because we already had M for mass, and there's I, which was out there, but I is going to stand for something else, and it would be confusing because impulse, like impulse engines in Star Trek, we'll talk about that. Impulse is something that is a core fundamental part of physics as well. So we didn't want to use I, so they settled on P for a linguistic reason. You can go down and read the article. I think it's super interesting, but I'm a nerd about scientific history. But back to Zane here. So we've got P equals mass multiplied by volume, multiplied by velocity. Not volume. We've been doing density in eighth grade. So P, momentum, equals mass. So the mass of this pumpkin, I don't have a scale here, I can't look it up, or the mass of Zane, Ninjago, Lego Zane, or the bad guy that he's fighting, this goblin thing. It has a pretty cool crossbow. Like you can actually shoot this crossbow. Let's see. Let's see if the momentum works. Whoa, that's fun. Don't tell my son I did that. So we have P equals mv. So momentum equals mass multiplied. I have to fix this or he's going to yell at me. He's a 5-year-old, but he's very, very peculiar about his Legos. Mass times velocity. Now, velocity is speed in a given direction, and most of the time we'll tell you, like, if we're doing a momentum problem, we'll say things like the speed of this pumpkin is rolling, down a hill at 10 meters per second easterly or something. And that's because we need velocity. And velocity is a vector, meaning that it has uh, the ability to have magnitude. So that's why we say P equals mv and not just speed. Um, Basically, for our class and for our intents and purposes, it's the same thing. But when you take physics in college, you'll learn there's a lot to be distinguished there. I can't do this. Between speed and velocity. So P equals mv. Remember, P in our class, for the most part, it's going to be measured in kilograms. So even our little goblin here, or Zane, or this pumpkin, it's going to be measured in kilograms, just to make it easier. You can do grams, but it's gonna make it a little more complicated later on, as you'll see. So I would stick with kilograms, and I think on the Khan Academy stuff, they stick with kilograms. And then our velocity is measured in meters per second. So acceleration is meters per second squared, velocity meters per second, not inches per second, meters per second. So kilograms times meters per second is the unit for momentum. We'll clean that up later. But for right now, it's kilograms times meters per second. And that's the big thing that I really wanted to make sure that you know. So momentum is kind of related to energy and mass because it's one of those things that we don't create or destroy. So even when Zane collides with this pumpkin, we have a conservation of momentum. Very important. And P equals mv is the main formula we're going to use here. Now, one thing I will warn you about with Khan, there's a lot of questions regarding the momentum of whether or not, uh, like Zane here and this pumpkin, when they hit each other, when Zane does battle with the pumpkin and his shield hits the pumpkin, uh, if they were to move in different directions, so if Zane comes in really hot, hits the pumpkin, bounces back, all that momentum that both Zane and the pumpkin have are conserved, but they move in different directions. So in the problems that you're looking at, what you want to look for is different symbols for the two sort of joined momentums. So when you have a system, so two things that are interacting, you want to look for opposite symbols. So you want one symbol to be negative, one symbol to be positive. And that's kind of the trick with the con questions there. And they really want you to get that, and they beat it into your head, which is a good thing, and you should get that. But sometimes you have a system where, say, Zane and the pumpkin are running into each other. The pumpkin is much more massive than Zane; it's pretty heavy. And as this pumpkin, this gourd, pumpkins have a very fascinating history, by the way. As this pumpkin runs into Zane, it's going to overpower Zane, and they're going to move as one system in one direction, right? And there's a way to calculate that momentum. And that's going to be all the same symbols. So when you get to those questions where it's like, find two equations that show the momentum of this system of two dogs bumping into each other, or a football player hitting another football player, or a lacrosse player hitting another lacrosse player, or Zane and Ninjago and a pumpkin hitting each other. And geez, I'm causing all sorts of issues here that I'm going to have to clean up later. That's what that's about. So look for the symbols, or in this case, the negative, positive, plus, minus signs. I should be doing Winnie the Pooh and Zane. That would be a much better fight, right? I think Zane would take this one, but Winnie is pretty vicious. Um, and that's the big thing. P equals MV. Look for your signs and conserve the momentum. If you have any questions, let me know. Hop on Classroom Q and ask away. Tomorrow we're going to go into more about impulse and some more advanced uh, type topics that we need to cover for momentum. But keep in mind, it's all related. It's all one big story. F equals ma, P equals mv. It's all part of the same system of us trying to figure out how these big things in this world interact and bump into each other and conserve momentum and conserve energy and conserve mass. It's pretty cool.